Hello everyone, welcome to the session. So now in this video, we will be starting doing the EDA part. I hope that before coming to this video, you already have watched my previous two videos where basically we have understood the data which we are dealing with. In the second portion, we have already prepared our data in a way that we will be having for every record a corresponding price value, which is the target value that we have, right? We have seen also in the last video that there is no as such null values which are there in our given data set. That's why there is no as such need of doing a data imputation, right? So now let's get started to see the statistical analysis of this particular data set. We are doing EDA. I hope that you already have a clear cut idea about EDA portion. Its full form is exploratory data analysis. As the name itself suggests, that here we want to analyze the data in a way that we want to filter out the quality content out of the given data. Obviously, the higher quality data or content that we have, you will be able to understand that the better accurate predictions we will be able to get, right? So, in the complete life cycle of any machine learning or deep learning or data science based projects, if let's say someone will ask you that where the developers will spend most of their time in the complete life cycle, no, it's not in model training, no, it's not in model deployment. The major time that they spend in EDA. Why? Because as I told you, the better quality of data we will be able to get, the better accurate predictions we will be able to perform afterwards, right? So in today's session also, we will spend most of our time in doing the analysis of the data. You will try to observe what are the steps required to perform in EDA. There are lot many steps depending upon what kind of data we are dealing with. But today I'll try to show you few of them, and we'll try to get the insights from that data, right? So until so far, if you will be able to observe, in the very first part, we have already understood the data, right? We have spent our time in terms of understanding the data values or data points that we have. In the second life cycle of complete project, we have talked about data preparation. Data preparation. After that, now we are talking about exploratory data analysis. Exploratory data analysis. And as I told you, this is one of the most important step out of all the steps that we will cover up. Okay? The very first thing that we will do in this EDA part is to find out the correlation coefficient value. Now, what is the meaning of correlation coefficient? Let's try to understand. In statistical terms, how we basically usually find out this correlation coefficient, you can go and refer the stats videos for that. But I'll try to give you the inference behind finding this correlation coefficient. First of all, if you will be able to observe, the value of this correlation coefficient will lie between -1 to +1. What does that indicate? This indicates that either the two variables that you have in a given data will be negatively correlated with each other, or they will be positively correlated with each other. Now, either it will be negative closer to -1, or it will be positive closer to +1. Both are not good for our data. Why I am saying so? Please try to understand. For example, let's say I am saying that we will be having two features. Let's say feature F1 is there. Maybe they are responsible for predicting the house itself, right? So let me try to plot it once. Let's say I will be having a feature F1, and here I will be having a feature F2. If I am saying that at any point of time, when the value of F1 is increasing, the value of F2 is also increasing. Means something like this. They're directly proportional to each other. At any point of time, what you are observing a trend is that at any point of time, when your value of F1 is increasing, for example, let me give you some real-time example. Maybe let's try to understand the relationship between the weight and the height of a person. So what we can observe, as the let's say height of a person will increase, it's a very simple example which I'm trying to convey here. You will observe the common form is that in the maximum scenarios, the weight of a person will also increase. So in this way, you can say that, okay, these two variables, these two features are highly correlated with each other, and that is in a positive direction because they're directly proportional, right? This is the meaning of highly correlation in a positive direction, means the value is approximately very close to +1. Now, what is the meaning of negative correlation? The simple meaning is that at any point of time, if let's say you will be having feature f1 and then you will be having feature f2, what you are observing is that as the value of f1 is increasing, your value of f2 starts decreasing. It's kind of an inverse proportion which you are observing here, that as the value of f2 is increasing, what you are observing, the value of f1 is decreasing and vice versa. Means value of f1 is increasing, value of f2 is decreasing. So this kind of format you're observing between these two features. Again, if you will be able to observe, in a way they are correlated, but now they are negatively correlated. Means in this case, in this scenario, their value is approximately equals to -1. Now, what in layman terms these things indicates? Let's try to understand this fact. It simply indicates that these two features are trying to give the similar kind of information. Please try to understand my statement. These two features are trying to give a similar kind of information which is responsible to give the predictions. So what usually happens is that, let's say we will be having features of f1, f2, f3, let's say f10. And let's say we will be having a target value which is available. Doesn't matter whether we are trying to solve a regression based problem or a classification based problem. But yeah, this is what we have. So we will be having a features and then we will be having a target values available. Now, when I'm saying that the feature f2 and let's say feature f9, they are highly correlated. They are highly correlated. Doesn't matter whether it's positively correlation or it will be a negative correlation. I am saying that these two features are highly correlated. Means they are trying to convey a similar kind of a pattern, similar kind of information which is responsible to give this target value, which is responsible to give this target predictions. So that's why what we usually do is we usually try to take only single feature at that point of time rather than taking all the features. So it's kind of a feature selection technique, you can say. This is a kind of a feature selection technique, right? Because too many features are not helpful if they are conveying the same kind of information. So rather than taking all the features, which will increase the complexity only, what we will do is we will try to select only those features which are giving me a very important information which not other feature is giving to us. Okay? So let's try to now focus and jump towards looking towards this correlation coefficient value. I hope that you will be able to understand my point. What is the inference behind doing the calculation of a correlation coefficient? I hope that now it is pretty much clear to each and everyone. So without wasting any time, let's try to do the calculation and the function calling for that. So what we can do is we will be having a data set dot. Now this is the function which is core. This function will basically helps me to give a chart, or you can say to give a proper feature names with respect to every feature. It will give in a tabular structure what is the correlation coefficient value. So this is the simple way to do the calculation, no hustle here. So here if you will be able to observe, once I will run this code, you will be able to see that all those features, same features, if you will be able to see, they are obviously highly correlated because med ink and med ink, they are both the same, and obviously their values will remain the same. It's kind of a +1. That's why if you will be able to observe diagonally, all the elements values are +1 only, because obviously they are highly correlated because they are having the same features only. But on the other hand, if you will be able to observe house age, mad ink, average rooms, house age, for every particular two features, now you will be having the values which ranges between the -1 to +1. In this complete table that we have, you just have to understand that is there any two variables, two features which are having a highly correlation coefficient. That is what we have to understand. Here if you will be able to observe, apart from this diagonal one which doesn't make sense for our code, when I'm talking about the independent features that we have, as of now I can't see any feature, any value which is having a very high positive or negative correlation coefficient. I think I am correct, but still if you will be able to get that at your end, you can let me know. But yeah, Here, as far as I can see, that there is no as such a feature which is having a very very high, like whose value is more than 0.80 or 0.85 correlation coefficient value. Maybe average bedrooms, you can say, and average rooms, they're having a highly correlation coefficient. It's 0.84. Usually 0.85 plus is considered, but it depends again on data set to data set, that you can try to see that if you will try to remove one variable, maybe average bedrooms, does that performance is impacted or not. But yeah, this number I can see here. Apart from this, any big number I can see? I don't think so. Okay, longitude and latitude. Again, they are having a very high correlation coefficient, right? Negatively correlated. Now here you will observe one thing, right? When we are talking about average bedrooms and average rooms, again, obviously they are conveying a similar kind of information only. In a given house, average number of bedrooms, average number of rooms are trying to convey the similar kind of information. That's why you will be able to observe they are having a very high correlation coefficient. Similarly, the same thing will go for longitude and latitude kind of a correlation coefficient, right? Apart from this, we can also create a pair plot which will be able to give us for all the features that we have, what is the correlation again they are trying to convey. So what you can do is you can take the help of this SNS library which we already have imported. You can say pair plot, and here you can pass data set. Now what will happen after some point of time, you will be able to see that there will be a complete end-to-end chart where for every two features you will be having a plotting that will also represent that what kind of distribution every particular variable or the feature that we have indicates. But until so far, what inference we will be able to get in the above cases, the first important thing is what we will be able to observe, that we have observed average bedrooms and average rooms have high correlation coefficient, and the value is 0.847621. I'm just writing it down. Also, we have observed that this longitude and latitude are negatively correlated with this number. So let me write it down this as well. Longitude and latitude, they are also negatively correlated. It's minus of this thing. Let's try to write it like this so that we will not get confused later, right? So it means that between these two features, average bedrooms and average rooms, and longitude and latitude, we can take a single feature also that will also work and will give us sound performance. Okay, we'll take care in this in future. Apart from this, I don't think that there is any other feature which is having a higher correlation coefficient. But still, I'm looking into it. Maybe we will be able to get any other feature. Meanwhile, I think the below code is running up, but I don't think we do have. Perfect. So here, if you will be able to observe, finally now we will be able to get a pair plot. Here, if you will be able to see, if I'll just zoom my screen, for every feature, for example, Madden is in the y-axis, house age is there, right? Average rooms are there, average bedrooms are there, population is there, average occupation is there, latitude is there, longitude is there, price is there, and then on the x-axis again there are feature names which are available. So what we will be able to get here is the graph for every particular two features that we have, kind of a pair plot. That's why it is called as. And you can see that whether the values are directly proportional or they are inversely proportional or they are scattered somewhere, outliers are there or not, all these things you will be able to see. For example, let me give you one simple example. What is the meaning of outlier? Some exceptional points are something which we can say is an outlier. For example, here if you will be able to see, corresponding to average bedrooms and you can say population, can you see the topmost two dots? I can apply the cursor here. Topmost two dots. So these two dots, right? So here if you will be able to observe, this is something which we called as the outliers, which you can see somewhere dots are there. Many points are surrounded by one region, and then there are 1-2 dots which you will see outside another region. That is something which we call as an outlier in every graph. Okay, when we're talking about these outliers, there is another way to detect that, and this is something that we called as a Box plot. Again, it's a concept in statistics, which is basically used to detect the outliers in a given data set. So how basically we will be able to do that? You will be able to say figure and the axis ax. You will try to call this plt dot subplots, and here you can define the figure size, like how much size of that subplot of box plot that you want. Maybe I want 15 comma 15. So you can refer that pretty well. Now what you can do, you can call this sns.boxplot. Inside this, you can refer what kind of data you want as a box plot. I want data set here, and the axis is ax, which I have already defined in the above part. If you want, you can also save your figures on the go. For example, if you will say plt.savefig is the command to save the figure values, and here you can say it is a boxplot.jpg. You can also save in the form of a png. Anything will work here. Just run this, and once you will be able to run this, you will be able to see that a complete graph is also available here. If you want, you can download this as well. Okay, and once this is downloaded, you can grab this in the downloads, and you will be able to see this is the box plot which we will be able to get. Right now, here again you will be able to observe that we will be having Medinc, we will be having house age, we will be having average rooms. In the x-axis, try to observe whatever with the values are there, right? Population is there, average occupation is there, latitude is there, longitude is there, price is there. One thing which you will be able to observe very clearly here is that, uh, all the values apart from population is lying under the range from 0 to maybe 500 maximum. I'm not sure, but the range is very, very small. Every other feature apart from population, and that creates again a bias, right? So what usually happens when we will be having something like this kind of architecture, please try to understand this from this box plot what I'm trying to convey here. So usually what happened is that you will be able to observe apart from population. So population is having a very bigger range. Just now we have observed. And that makes sense also because we are talking about that in a particular block, what is the amount of people living there, right? So population is having a very huge range of numbers. That is what we have seen in the box plot as well. And even this population contains outliers also, which you have observed. They contains more outliers. So here, if you will be able to see how you can detect those outliers, if you will be able to see all the points above this line, dash line. So this above dash and below dash is a range. Outside this range, if there is any dot, any data point which is available, all those data points will be considered as an outlier. Okay. So now the important point here is that we have to somehow manage these outliers. Either one way is you can remove these outliers in a simple go, but obviously that includes a loss of data points. Other way is you should know the concept of quantiles. Within 95% quantile, you can take the data points, and remaining you can get rid of. That will try to remove the major outliers present in your data set. Few outliers, if they are there, that is completely fine because they can act as a noisy points, and it will make your model more better in a way that it will be able to detect that okay, these are the noisy points, and I don't take those points in a prediction part. But more of them is not something which is recommendable. Now here, if you will be able to observe this data point, when we are talking about this population, they have a very huge range of numbers, whereas the other values like average number of bedrooms that we have or average number of rooms that we have, although they are representing the similar information that we have seen from the correlation coefficient, or we have something called as mad inc as the feature name, or we have something called as a house age as the feature name. All these are somewhere surrounding within some specific range, but this range is very, very high. Now what usually happens when you directly impose this kind of a data set directly to the model, maybe what we will do is in the future we will apply a linear regression model here, right? Or maybe any machine learning model. Today we are discussing the machine learning model as a linear regression, but in future we will discuss more models also, right? So what I'm saying is you will apply any machine learning model here. Maybe today we are applying a linear regression. So what happens is that our model will get biased towards treating population feature as on priority. As on priority, it will give more priority towards population values because the numbers are very big, right? So it will automatically inferent that okay, population is having a very big range of numbers, might be this feature is having a utmost priority as comparable to other features, but that is not true. All these features, apart from the features that is having a very high correlation coefficient, apart from that, all those features are having a equal relevance in order to give the predictions. So what we have to do is, in that scenario, we need to avoid this bias. We need to avoid this bias problem. And to avoid that bias problem, we need to do a standardization. Or you can say you need to do a normalization of all the values that we have. We need to do a normalization of all the feature values that we have. All the feature values that we have. So what usually happens is that we will try to scale our values in between some specific range, all the values. And that is where we have two methods. One way to scale the values is via using a standard scalar. Standard scalar. Another way is you can use a min-max scalar. Min-max scalar. Now, what I will do is I will try to do with the standard scalar as of now. What it will do is it will try to convert all the values in a standard normal form. In a standard normal form. Now, I hope that everyone knows what is the meaning of a standard normal form, where the mean value is 0 and the standard deviation value is 1. So this is what we will try to do. We will try to convert and scale our values in the form of a standard normal form by using the standard scalar. So this will help my complete data points within a scale, within some specific scale. So that is where what we will try to do is we will try to scale our data points. Now, to do that, what we will do, we will try to first of all split our data points into two important components. One is the independent features, another one is the dependent features. So what we will do is, we will try to do one thing. We will try to split the data into independent and dependent features. So what we will do, I'll take the variable x. There I'll take the data set completely, apart from the last column that we have, which is price, right? So what I will do is I will try to take all the rows and I'll try to take all the columns except the last one. This is x. What is y, which is the target one? Here I'll try to take dataset dot ilog, right? We are taking with the help of the index numbers that we have. And here I'll try to take all the rows and only the last column. Okay? So let's try to see what we will be able to get from this part. If you will be able to observe the value of x, you will be having all the rows, all the columns except the last column, as you can see, because we have taken all the rows except the last column. Let's try to show you the value of y as well, which is a dependent feature that we have, which is the price. And here you can see we will be having the price values available from 0 index to the 20,639 index. Now, what we can do here is we can try to split our data into training and testing, and then maybe we can do the scaling process. So what we can do is we can split the data into train and test set. So what we can do is we can try to say from sklearn underscore model sklearn dot model underscore selection. What we can do is we can import here train test split, because we want to do a split here in the form of our training and testing set. So what we can do, we can say x train, we can say x test, then we can say y train and the y test. Now what I will do here is I'll try to say train test split, and inside this what I'll take is I'll take the value of x completely, the value of y completely. What is the test size you want to take? Maybe I want 30% of my split is in the test set and remaining 70% will be available in the train set. After that, if you want, you can also define the random state so that we all will get similar kind of a output. Let's say I will take a random state as maybe 42. so that we will be able to get the similar answer. Importance of this random set variable is, for example, if you will not apply this random set at each and every point of time when you will run this code, you will be able to get a different set of a training data, different set of a testing data. If you want to fix that number, that you will get at every time when you run the code, similar set of a training and similar set of a testing set, so that's where a random set will come into picture. You can apply this with any number, 42, 144, 146, any number, and you will be able to get that set value. Okay. Once you run this, let's see what our training data will look like. Perfect. Now you can see how our testing set will look like. Shift plus enter will be required to run the code. Similarly, you can see how basically your Y train will look like corresponding to those training sets. You will be having the price value. Similarly, you can test how this test set will look like. Corresponding to every test value, you will be having the value of a test set. Now, what you can do is, now here comes the step of doing normalization of the given data points. Normalization of a given data point. So what I will do is again, this is a part of a pre-processing. So you will say from sklearn dot pre-processing. What you will do is you will import standard scalar, because that is what you want to do. You want to scale your values in the form of a standard scalar form, right? So you will call this function and store this inside the variable standard scalar. Okay. And then finally, what you will do is you will say x train. You can say norm, because you will be able to get the normalized values. What you will do is you will try to take your scalar dot, you will use this function fit underscore transform, and inside this you will call your values x train which you want to transform. This will help your values to fit or to scale within a specific range. I'll show you the same thing as well. Now, if you will be able to observe this x train underscore norm value, you will see the difference. Can you see a specific range is there? In more clear sense, let me try to again do this box plot and will try to show you the range now, because you will now when we visually see the things now, then we will be clearly able to understand what things are happening. So I'll try to show you x train norm box plot of a train data. Let's see. Can you see a big difference is there, right? Now can you see all the boxes in the box plot lie in one range? Can you see that? There is a gap between this chart which we get now and the previous chart that we got, right? There only the population is having some another level, remaining are of similar level. But now if you will be able to observe it visually, you will be able to see a huge difference. A huge difference is there, right? Although outliers are there, we will discuss in the upcoming sessions that how we can deal with the outliers. There is a complete concept of quantiles which I will taught, and then we will see that how we can get rid of these outliers. But as of now, I'm not focusing on that aspect. I'm focusing on that how basically we will be able to scale the values so that our model will not be biased towards any single feature. That is the ultimate thing which you have to understand it here until so far, right? Now here, if you will be able to see, I have used one function called as fit underscore transform. In the test set, what usually happens is you have to use a function called as a only transform, scalar dot transform. And here what you will do is you will use this on the x test. You can say x test underscore norm. So this is the normalized values of a test set, similar to the one which we got as a train set, right? If you will be able to see, the similar plot you will be able to get for the test set also, the box plot, x underscore test underscore norm, and here you can say box plot of a test data. If you will run this, now again you will see a similar kind of a distribution will be there, where the range of every particular feature that we have is quite same, right? So we will be able to normalize our data values, our feature points within some specific range. That is what we have understood here. Perfectly fine. Perfectly fine. One thing now, if you will be able to observe, is that in the train set, when we are doing the normalization, I was using a function of fit underscore transform, right, on the training set that we have. Whereas in the test set, when I was doing the normalization, I have only used the transform function. on the test data. Now, in an interview, interviewer can ask you why usually this happens. That in the training set, it's always recommended to go and use fit underscore transform function when we are doing a normalization. And on the test set, it's recommended to go for a transform function. What is the significance for that and why we are using this kind of a thing? So I'll talk about this particular thing in the next upcoming session. I think this session is already quite long, but this is your assignment task. Please try to explore that why I am doing so. On the training set, I am using a fit underscore transform function. On the testing set, I am using a transform function. And we will continue from here itself in the next upcoming session, where I'll discuss about the reason behind the same, and then we will further move towards the model training part, where we will see that now once we will do the EDA part, how we will be able to apply the model training, the linear regression algorithm on the top of this kind of data set. I hope that you are enjoying this complete session because it's complete practical session, and I am doing all the code demonstration also in the live part itself, so that no one feel bored here. If you still have any sort of doubt, do let me know. I will for sure try to resolve it as soon as possible. With this, happy learning to all. Bye bye, everyone, and I'll see you all very soon in the upcoming sessions.